Hey everybody, this is Bharat Muthuswamy.
And Amir Muqtadari.
This lab is on building a square wave generator or a relaxation oscillator using operational amplifiers. It illustrates an application of positive feedback.
So let's get started.
In this lab, we'll analyze the circuit shown. Note that this circuit has both positive and negative feedback. A common explanation you may have heard for circuit functionality is the capacitor C1 charges and discharges through feedback resistor RF. The circuit's output voltage V0 switches between VDD and VSS depending on the trip point set by R1 and R2.
But then why does this circuit behave as an oscillator? More specifically, will it still behave as an oscillator if you replace the capacitor with an inductor? Will it still work as an oscillator if you swap the inverting and non-inverting terminals of the op-amp?
Great questions, Amir. You'll be able to answer your questions at the end of this lab, but first, let us understand the problem at hand. Step one is understanding the problem. As usual, let us start by looking at the crux of the problem. The crux of the problem is again to separate out the statics from the dynamics. Note that the operational amplifier is a static device. There are no dynamic elements associated with it. Hence, we will analyze the op-amp circuit first and then analyze the parallel combination of the op-amp circuit with capacitor C1.
Is the NR the symbol for a nonlinear resistor?
Correct. I use a nonlinear resistor symbol because of the effect of the operational amplifier rail voltages.
So we will first derive the IV characteristics of the op-amp device.
Correct. So let us now devise a plan of action. We will first derive the IV graph using the op-amp rules, like Amir correctly pointed out. Next, we will impose this dynamic constraint from the capacitor.
So the negative sign in a capacitor IV relationship is because of the passive sign convention?
Exactly. And as usual, why don't you, Amir, do the derivation of the IV?
Okay, from the op-amp schematic, I can actually find some general relationships that are true, irrespective of the op-amp operating region. For example, Ohm's law across resistor RF gives I as a function of V, V0, and RF. Also, because the current into the non-inverting and inverting terminals of the op-amp are always zero, I can find Vp as a function of V out by using a voltage divider. We now impose the conditions for each of the operating regions of the op-amp: linear, positive saturation, and negative saturation. In the linear region, we know Vp equals Vn. But since Vp equals 1/2 of V out, since R1 equals R2, and I equals V minus V0 over RF, and you can recall that from the previous slide, we simply get I equals negative V over RF. Plotting this function, we get the straight line shown over here. Note that we do not know the limits of the linear region of the operation for the op-amp. To find that out, we use the saturation regions, starting with the positive saturation. In positive saturation, we know V out equals VDD when Vp is greater than or equal to Vn. Now, since we know I as a function of V out, we simply get I equals V minus 9 over RF. And since Vp is 1/2 of V out, which is 4.5 volts, and Vn equals V, we simply get the condition for positive saturation as V less than or equal to 4.5 volts. Plotting the function, note that for positive saturation, I is negative.
Negative saturation works the same way as positive saturation. Notice how that the current is positive when the op-amp is in negative saturation. Also notice how the completed op-amp IV is not a straight line, rather the function is piecewise linear and overall nonlinear.
Now that we have our static IV for our nonlinear resistor, we will impose the dynamic constraint from the capacitor, I equals negative C dV dt.
I'll take over now, Amir, and clarify the concepts of equilibrium points and dynamic route. The reason is you may have heard of equilibrium points, but not of dynamic route.
Yes, I have heard of equilibrium points, but not dynamic routes. So equilibrium point is when the capacitor is fully charged and the current through it is zero.
Correct. And that is exactly what this black point is on the graph. The powerful technique of dynamic route is used to graphically predict the change in voltage and current, and hence the term dynamic route. Route imposed by the dynamics of the system. This technique was pioneered by Chua, Desor, and Ku. Anyway, the idea is you see how a small change in I affects the sign of dv dt. For example, going back to this equation, if I is positive, since C is positive, dv dt is negative. Notice the arrows on the graph. The arrows in the linear region, that is when the op amp is in the linear region, point away from the equilibrium point because, for example, down here, I is negative, so dv dt is positive. In other words, I'm increasing in the value of V. Increasing direction of V is given to the right. So that's why this arrow points down. Similarly, when I is positive, going back up here, the dynamic route says dv dt is negative because C is positive. That means I'm decreasing on V, and in this region, I'm moving towards the left. Since the arrows move away from the equilibrium point is unstable.
Okay, now I see the justification for the arrows in the two saturation regions. But the arrows from the linear region and saturation region collide at the points you have labeled as an impasse.
Exactly. And the system cannot stay at these impasse points because guess what? These impasse points are not equilibrium points. The current at the impasse points is non-zero. Therefore, what the circuit does is it switches state along lines of constant voltage because V is the voltage across a capacitor and it cannot change instantaneously. In other words, as the circuit switches between the two saturation regions, V0 oscillates between plus or minus 9 volts. The energy for this switching comes from the op-amp power supplies. This is actually the reason why the circuit is called a relaxation oscillator, because of the ultra-fast switching dynamics between the saturation regions and then the slow relaxation dynamics within the saturation region.
Wow, so I can now find the period. So I simply write the first order RC equation in the saturation region, since I have only a resistor in parallel with the capacitor.
Correct. Be careful of initial conditions though.
No worries. I will simply compute the time the circuit spends in one saturation region and double the result. Doing so, I find the period to be shown here. This is exactly what is derived using more complex techniques. Also, I can easily handle the case when R1 is not equal to R2. I guess we can now move to the lab demo.
Exactly, Amir. So it's lab demo time.
So here is the lab demo. As you can see, we've set up the TLC 277 op amp to make a relaxation oscillator. You can also see the resistors and capacitors set up. Over here with our DC power supply, we're supplying rail voltages of positive and negative 9 volts, as you can see. That should give us a rail-to-rail voltage of 18 volts. But when looking at the oscilloscope, you can see that our voltage peak to peak is not quite the 18 volts that we expected, but that's completely normal because we know that the TLC 277 is not a rail-to-rail op amp. So we can also see that the period we are getting is 4.24 milliseconds, which is slightly less than the calculated value of 4.39 milliseconds. But that's also expected because we know that the op amp is not a rail-to-rail op amp, so the switching happens a little bit faster than a theoretical value.
Based on the lab demo, we can conclude that the physical realization of the relaxation oscillator does indeed show V0 of t varying between approximately plus or minus 9 volts. It's because, again, like Amir mentioned, the TLC 277 is not rail-to-rail. We also confirm the period to be very close to 2 ln 3 times RF times C.
Now, I should be able to answer questions based on different kinds of op amp oscillators.
Correct, Amir, but it turns out that only one of these proposed circuits is an oscillator. The other two circuits' functionality can also be described in one word.
Okay, I'll definitely work on it. This is fun stuff.
Sure is. Next time, we'll work on a family of different kind of operational amplifier circuits called filters.
See you then.